the cardinality of x is strictly greater than the cardinality of y, then f cannot be a one-to-one function. It cannot be an injective function. Okay, so what it's saying is that if I have sort of a larger set x and a smaller set y, and I define a map from one to the other, then if I look at the various points of x, at least some 2 points of x have to go to the same image, right? And it's obvious, the statement, because in some sense there isn't enough space in y. If every element of x had to be mapped to a different element of y, then y would have to have at least as many elements of as x. Okay, so since we have the opposite hypothesis that x has more elements than y, this function cannot possibly be 1. So this is one of the various ways of formulating the Pigeonhole principle. Sort of a more common formulation, which is what we often use in these sorts of counting problems, is say if there are n boxes, if there are n boxes into which we have to put m things, with m more than n, or more things than boxes, then some box has 2 things. Then there exists a box containing at least 2 things. Okay, so this is called the Pigeonhole principle. The pigeonhole just refers to the various boxes, or mailboxes in which you put letters. If there are more letters than boxes, then some box will have to have 2 letters. So here are the various sorts of applications. So let's start with some easy ones. So suppose I have, so here's the first problem. An English sentence has, let's say, an English sentence with 27 words. Must have at least 2 words which begin with the same letter. Words with the same starting letter. Is this fine? So how does one? So let's just quickly see what's the argument. How do you do this? Just unmute and speak.
There are 26 boxes.
Yeah, so there are 26
boxes. Corresponding to each letter, we can take a box. So number of folds are 26 and pigeons are 27. So there must be at least one hole receiving the more than one word.
Oh, more than one word. Okay. So you in this case the formulation is to say, okay, let's look at the 26 boxes. Let's first form 26 boxes. All words which begin with A in the sentence you put into the first box. All words beginning with B you put into the second box, and so on. So there are 26 boxes. So you scan the sentence, and as you read each word, you put that word into the correct box. Okay. So as you keep doing this, what will happen is maybe there is some word which you put into the which begins with A, another word which begins with B, and so on. But at some point, there are 27 words in all, and there are only 26 possible holes or boxes. So it's by the Pigeonhole principle. some box somewhere must have at least 2 of these points. Okay? So that's really okay. Now there are many other versions of this principle. I mean, it's one of those principles which is often not worthwhile formulating in some very precise form, because it can appear in various variations with the same basic idea. So here is another instance of this. So suppose I have 2 subsets. So let A and B be subsets of the numbers from 1 to 100. A is some subset of numbers from 1 to 100, B is another subset. And suppose I know the following, that I don't know the individual sizes, but I am given that the size of A, the cardinality of A plus the cardinality of B is at least 101. Okay, then prove that there exists a number in their intersection. So there exists a number A, or let's just say it this way, prove that the intersection A intersection is so how do we do this? I mean, if you don't want to use a pigeonhole principle but think of it in other ways, that's fine too. Whereas also we talked about inclusion exclusion last time, and this problem can also be done using the inclusion exclusion sort of thing. Any suggestions?
The given condition will be satisfied whenever one of the set containing the 51 elements, at least 51 elements.
Okay.
Okay, and if the one set containing 51 elements, so other is minimum contain the 50. Other contain 50.
No. If this contains 51, then the other.
Then other contain the 50. If I'm taking the minimum sum as a 101.
Correct. Yes.
So one set is having 51 numbers, another set having the 50 numbers, and there are total 100 numbers. So it means that there will be at least one number which is present in both the set.
Correct. Okay. Absolutely. That's right.
But so otherwise, we can use the inclusion exclusion principle.
Okay. So
suppose if the intersection is empty, okay, then we get a cardinality of.
If the intersection is empty, then
cardinality of A union B is greater than or equal to 101. Because this is equal to cardinality of A plus cardinality of B.
Cardinality of A union B is the same as cardinality of A plus B minus A intersection B in general. Yeah. A intersection B is 0. So this is just A plus B.
So that is greater than or equal to 101.
Correct. So in this case, the cardinality is actually 0. And this is given to be greater than or equal to 101. Why is that a contradiction?
So we know that the intersection is empty.
Yeah,
and therefore both A and B.
No, so you finally obtain the following fact: the cardinality of A union B is at least 101. Correct? Now, but why is that a contradiction?
A union B is a subset of X.
Correct. The set X, which is the original set here, A union B is a subset of that set. It contains numbers only from 1 to 100, right? So the cardinality can't be more than 101. It's at most the cardinality of X, which is 100. Right? So this is by the inclusion exclusion principle, but you can of course think of it similarly. It's analogous to the pigeonhole principle in the following sense that so suppose I have so think of it as follows. So I have this set A. So let's see what is this. So I have the numbers from 1 to 100. Okay. Now, if I do the following, so I have these numbers here, and now I have my set A and my set B. Right? I don't know what my sets are, but let me do the following. So I just look at this list from 1 to 100. Whichever numbers belong to A, I will put one cross below it. So, for example, if A contains the numbers 1, 3, maybe it contains 51, and so on. So, whichever numbers belong to A, I will put a cross below. So, let's not take 51. I mean, it doesn't matter, 75. So, I put a cross below those numbers, and whichever numbers belong to B, I put, let's say, a tick mark below those numbers. Right, like that. Okay, so now when I look at the total number of symbols here, so the total number of numbers is only 100, right? There are totally 100 possible numbers. And if I look at how many symbols I have, crosses or ticks, that's how many symbols do I have?
Coordinate FA plus coordinate AB.
Cardinality of A plus cardinality B symbols, right? Because I put crosses for elements of A and tick for elements of B. So total number of symbols that I have is exactly cardinality of A plus cardinality of B, right? But the total number of symbols is given to be at least 101, right? So from the given hypothesis, I know that the number of symbols, cross or tick. So maybe I should just put cross for both. Let's just put crosses for both. So if something belongs to A, I put a cross. If something's in B, also I put a cross under it. So number of crosses is exactly cardinality of A plus cardinality of B. So at least 1. But now you can see that it's like the pigeonhole principle, right? So I have these 100 pigeonholes. I have the boxes from 1 to 100. In each box, I can put some crosses, or I need not put any crosses. But the total number of crosses that I'm distributing among these 100 boxes, I have to distribute 101, at least 101 crosses, okay, amongst only 100 boxes, which means that there is at least one box which has 2 crosses. Okay, is this? So I hope this explanation is clear. So this is just another way of thinking about the same thing. So it's really inclusion exclusion, but we're just framing it in terms of the pigeonhole principle. So roughly philosophically speaking, we should think of pigeonhole principle as saying somehow when there is not enough space, there will always be overlaps. It's a sort of an intuitive way of thinking about it. You always must have things overlapping if there isn't enough space for all of them to sort of be placed in a disjoint. Okay, so that's just various avatars of the pigeonhole principle. So here's the next problem. Okay, so problem 3 says, let n be a number that's at least 2. Okay, prove that there exists a multiple of n. Let's call this multiple capital N. There is a multiple n of n such that which only contains zeros and ones in its decimal expansion, which contains zeros and ones, meaning it need not have both. It could have all zeros or all ones. That's also okay. There exists a multiple n of n, which contains, so this multiple is also talking about positive integers, which contains only zeros and ones in its, when you write it in its usual decimal expansion. Okay, so I hope the question is clear. So let's just do some examples here to sort of make it even clearer. So let me pick various values of n and see which multiples satisfy this property. So for example, if I take n to be the number 2, then which multiple of 2 has the property that its decimal expansion only has zeros and ones? What's one example? Is the question clear? So I want to say, given a number small n, show that you can find a multiple of small n, okay, which I'm calling capital N, such that that number, when you write it out in decimals, only will have 1 and 0 as digits, no other digits will have. So any multiple of 2 which has that property?
$10.
Yes, absolutely. So 10. So let's take 10. Okay, see 10 only has 1 and 0 in it. Okay? And that's a multiple of 2. Okay, great. 3. Which multiple of 3 has that?
1, 1, 1.
1, 1, 1. Excellent. So look at the number 111. That is divisible by 3, right? As we know, the test for divisibility for 3 is that you just add up the digits and see if it's a multiple. So 111 is of course 37 times 3. That's an example. 4. What multiple of 4?
100.
Up. 5 again, certainly 100. In fact, even 10 will do the job. 6. So remember, we have solved the problem for 3, so we have to use that cleverly. Otherwise, of course, we scan through all possibilities for 6 will be wrong.
1110.
Wonderful. 1110. So if you find an answer for 3, right? So this is a multiple of 3. All you have to do is just multiply that by 2. That's what you initially think of doing. So 2 to 2 would have been an answer, except it has 2's in it. So you don't want that. So the next best idea is you multiply it by 10. 10 has a 2 anyway. 10 is 2 into 5, right? So this, for example, is 37 into 3, whereas this is 37 into 3 into 10. And 10 is just 2 into 5. So you can see it's now become a multiple of 6. Okay, so 7, for example. Slightly tricky one if you haven't seen this thing before. So it's 1001. 1001 is actually a multiple of 7. Okay, let's check. What's 1001 equal to? So it's divided by 7. So 7, 7 ones are 7. So I have 1 left over. So that's 30. 7 4s are 28. 21, 43. So it's 7 into 143. And of course, what is 143? 143 is 13 times 11. So this is, in fact, it's actually a nice number. It's 7 into 11 into 10. Okay, so 1001 is actually 7 times 10. Okay, so so in fact we have solved the problem for 11 and 13 also incidentally by doing this. Okay, so and so on. So I will, you can imagine that one can do this. Maybe you can look at various things to simplify ways of doing this. For example, if I know the answer for 7, then by the same trick we used earlier, you can find answers for 7 into 2, which is you just take the previous answer and multiply by 10, for example, or things like that. So there are many nice things you can do. So I would suggest sort of exploring what's what are the various possibilities you can get and so on. But the question is somewhat vastly more general. It says, given any number n, I can always do this, right? I need to prove that no matter what my number n is, you can always find the next, a number containing only ones and zeros, such that that number is a multiple of n. It's rather somewhat counterintuitive when you first hear this, right? So I mean, I wouldn't believe a statement like this the first time we see it, because it seems somewhat strange. Why should it be possible to only use zeros and ones? Okay, but let's prove it. So here's the proof, and it's a beautiful application of the Pigeonhole Principle. Okay, so it's the following. It says, consider the following numbers. Okay, so this is the first step, which is somewhat how would you come up with this first clever step? So it says the following: consider the numbers which have only ones in them. Okay, 1, 11, 111, 1, 1, 1, 1, and so on. So look at this sequence. Okay, at the moment it's an infinite sequence of numbers. Now let's do the following. Let's take each of these numbers and find out what their remainders are modulo n. Okay, so if you remember what this remainder modulo a number is, you take each of these numbers modulo n, which means you find their remainders when you divide these numbers by n. Okay. So, okay, I don't quite know what n is in this case. So when I divide each of these numbers by n, I will get some remainder. Okay, so maybe we'll do it in some particular case. Suppose I take each of these numbers and divide them by 7. So what are the remainders I get? So for example, the remainder I get in the first guy, 1 divided by 7, remainder is 1. 11, when I divide it by 7, the remainder is 4. 101 when I divide 111 when I divide by 7, what's the remainder? 98, right? What's the multiple of 7 here? 7, 1. So what's the remainder here? Anyone figure it out? So I want to divide 111 by 7. I'm asking for the remainder.
6.
6. Okay, and the next fellow will be, what am I doing to this? I'm multiplying this by 10 and adding a 1. So the next remainder is really 61. It's one way of computing it. But 61 is like saying 5. 7, 8 are 56. Okay, and so on. So you can see all I'm doing is just computing the various remainders. So let's maybe just do a couple of steps. I'll tell you the next few answers. 1, 1, 1, 1, 1. So it's 51, so it's 2. The next remainder is actually 0. And so on. Okay. So I just write out all the remainders modulo 7. So in this case, you see, you already found a number which is divisible by 7. Okay. If you take the number with 6 ones in it, that turns out to be divisible by 7. Okay. So there, if you find a number like that, your problem is done, because that all ones is okay. So that solves your problem. But in general, suppose I try doing the same sort of argument modulo n. I compute all the remainders. N can be any number, 2 or more. Now here's what I will find. Okay, so I will get some remainder for the first number. So this is some remainder. Let's call it remainder R1 for 1. This remainder is R2. If we have 2 ones, the remainder is R2. Let's say. Then this is some other remainder, some other remainder, some other remainder, and so on. I keep getting all the different possible remainders. I mean, I may or may not get different remainders. I don't know. I get some remainders when I divide by n. Okay, but here's the question. So just like we did in the previous case of 7, if you look through this list of remainders, firstly, what all can be observed? What are the possible values of the remainders?
Any value from 0 to n minus 1.
First observation is that the remainders Ri can only take values from 0 to n minus 1. Okay, so there are only n possible choice of remainders. Okay, so that's the first observation. But this sequence that I'm writing here is well, it's an infinite sequence more or less, right? So I have a really infinite sequence of numbers. So when I keep writing the remainders, what am I certainly going to see at some point? So as soon as I have, let's take I even know at which point I will start seeing the repetition. So I keep going till let's look at the number 1, 1, 1, 1, 1, which has n plus 1 ones. Okay, so take that particular column of the table, n plus 1 ones. So this is the remainder r n plus 1. Okay, so look at just this portion of the table is enough. Now, what am I going to see when I look at these n plus 1 entries?
There will be again one number before that n plus 1 times 1 whose remainder, and we have the one n plus 1 times whose remainder is the same. And if we are taking the difference of that two numbers, okay, the difference is divisible by n, and
Okay.
if we observe the difference between these two numbers, it is consisting of only the digit 1 and 0.
Okay, great. So the pigeonhole principle now applied here is the following. So the possible values of the remainders is only the numbers from 1 to 0 to n minus 1, the n possible values. But I have n plus 1 remainders here. I mean, I have n plus 1 terms here. Okay, R1, R2, Rn plus 1. So now where is the pigeonhole? How are we going to frame it in terms of pigeonhole? So let's look at the different remainders possible. Those are going to be our pigeonholes 0, 1, 2, 3 till n minus 1. Now, when R1, whatever be R1, I will put it into that box, okay, whichever that number. So if R1, so in the case of 7 uniper, it was 1, 4, 6, 5, and so on. So whatever that R1 is, I'll put that into that corresponding remainder box, So maybe R2 is something here, R3 is something here, and so on. Okay. So the point is, I mean, if I get a 0, then I'm already done. But even if I don't, if R3 is here, etc. So the possible remainders are here. But the pigeonhole principle, PHP, says that there exists two remainders which must be the same, at least greater than or equal to 2 of these terms among the numbers R1, R2, Rn plus 1. Among these among these n plus 1 remainders, there must be at least two remainders which are equal. Okay, so let's call those two remainders something. Say Ri and Rj are equal. Okay. Now, if that is the case, then what does it mean? So recall that this just means Ri and Rj are equal means Ri is the remainder when we take the number 111 with I ones. Okay. So how do we write this in terms of congruences? You say this is congruent to Ri modulo n. This is the remainder, right? But on the other hand, the same is true with j in place of I. So if I put 111 with j ones, that's congruent to Rj modulo n as well. But these two numbers are the same by assumption. Ri and Rj are the same. So what does this mean? The number 111 with I ones and the number 111 with j ones are actually congruent to each other modulo n. So 111 with I ones, this number leaves the same remainder as the number 111 with j ones divided by n. But if two numbers are congruent, it means n divides their difference. So let's assume j was bigger than I. I can always suppose that j is the bigger index. Assume without loss of generality that j is the bigger index. Then n must divide their difference. Now, what does the difference look like? It's a string of j ones. Right? This is more ones, and this has fewer ones. So when you subtract, you can just see what will happen. I will get j minus I ones, followed by I zeros. Right? This is the number I will get when I subtract two numbers of this. Okay, so this is fine. So we have proved what we wanted. So this number you can take as your number n. This is the multiple of small n, which only has ones and zeros. So we have demonstrated one such multiple exists. And this is for all n. Okay, so any questions on this proof? Okay, if not, let me just ask a slight modification of this. What if I had said, so here's problem 3 part B maybe. Suppose instead of saying 0
So
and
this
1.
is a minimum number?
No, not necessarily. We have only demonstrated one number. This need not be many. Right? So we just had to prove there exists one number, so we have sort of exhibited that such a number exists. Okay, but the question is, so I'm just going to modify the question. If I replace, so I want to do the following, replace in the question, instead of saying zeros and ones, can I replace it with ones and twos? Then is it still true? Okay, so is the question clear? So what I mean is, if I want to say, given any number n, small n, is it true that there exists a multiple capital N which only has ones and twos instead of zeros and ones? Is it even true? So let's, so maybe you can just try out some examples and tell me if you think it's true or not. Is it possible to find multiple with only has ones and twos?
If we take multiples of 5, if you take n equal to 5,
okay, excellent.
We cannot write.
Okay, excellent. So let's do this. Suppose we take small n equals 5, then there is no such multiple capital N. Why not?
Because the unit digit is always 0 or
5 or 5.
Or 5.
Exactly. So observe that any multiple of 5 has units digit. Units digit is either 0 or 5. Okay. So that's not going to work because we are saying we only want ones or twos or both to appear in your number, but the units digit is 0 or 5. So definitely 5 is not going to work. Okay. If you take little n equals 5, then you are not going to be able to do this. Okay. Let's see. What about? So what if we rule out 5? So let's say, suppose let's do the following. Let's not allow n equals 5. Let me say I take numbers which are, let's say, relatively prime to 5, or maybe let me even make it slightly simpler. So sum of 5 is a problem. That's what we are observing. So I don't want 5. So if I have 5, then maybe some other multiples of 5 may also have problems. Okay. So for example, any multiple of 5 will have a problem. Similar, because we take 10 or 15 and so on, all their units digits will have the same problem. So multiples of 5 are all going to be problems. So let me say, if I take n to be, let's say, let's even make it a prime number not equal to 5. Suppose I say n is a prime number that's not equal to 5. Then is it true? So this is additional. So okay, additional hypothesis. So I'm going to say, let me assume that n is a prime number and it's not equal to 5. Then can I find a multiple of n which has only ones and twos in its decimal expression? So question, does that exist? I'll make it even simpler, multiple capital N of small n, which contains only only ones. Let's even forget twos. Is it possible to find a multiple of n which has only ones in its specification? So remember, you were able to do that for 7. We were able to find an example, right? So here was for 7, the multiple 1 1 1 1 1 1 is the number with 6 ones in it. That was a multiple of 7. So similarly, I want to know for other prime numbers. So if small is a prime number other than 5, can I find a multiple which has only ones in it?
Yes.
Right?
So first we got to work with the 0 and 1, and then add that number 2 times. You'll get 1 and 2.
Sorry. Say that again. First, you have to work with 0.
So we know that there is a integer n, capital N, is a multiple of n, and then the digits are 0 and 1. And then add that number, capital N, 2 times. That is n plus n.
N plus n will just have 2's and 0's. No? See, this n plus n is just multiplication by 2.
Yes.
So what will happen is that the 2, you just get 2's and 0's. Right?
Yeah.
Okay, so you have, if it's 1 1 1 1 0 0 like that, you add it to itself, all these ones will become 2's. So I mean, your idea is fine. You want to somehow add ones on the places where there are 0's. But if you add n to itself, that will not happen. It will only keep adding the ones with themselves and the 0's. Right? But I want, even forget the 2 also. So I actually want to even analyze just what we did earlier. If I just keep writing a string of ones, then, okay. So let me tell you the answer. Here the answer is yes. You can actually find a multiple which only has all ones in it. Okay. And why is that? So let's just analyze the proof a little bit. So we can actually get a little bit more from the proof. So what did the proof finally do for us? We said the multiple that we got was the following, right? So I'm just going back to the earlier proof. There are at least 2 numbers which leave the same remainder. I take their difference, and their difference becomes a multiple of small n. Okay, but then there is something more here which we haven't used so far, which is that this multiple capital N has a very special form. Okay, what does it look like? It's firstly all ones followed by a set of zeros. Right? So it's of a very special form. So let's see whether we can use that special form somehow. Okay. So let me start here. The answer is yes. Okay, why? Let's by the previous argument. There exists n of the following form: some number of ones followed by some number of zeros. Okay, which is a multiple of n, such that n divides n. So I'm just using notation for this bar in the middle just refers to division. N divides capital N, or capital N is a multiple of small n. Okay, so this is what I know. I know that there is such a number. Okay, but observe, this is a very special number, right? What is this? This is a string of ones. So take the ones alone separately. And what am I doing to that string of ones to get this number of
multiply with 1 followed by I.
Correct. Some power of 10, right? 10 power I actually. So this has j minus I ones, as we said before, and this is I zeros. So what is that? It's like multiplying by a power of 10. I'm just multiplying the answer by 10 power. So in fact, I know that capital N has a special form, string of j minus I ones multiplied by 10 power I. Okay. But now, this number is a multiple of this little n. Little n is a prime number. No? Okay. So let's try to use some properties of prime. So n is a prime number. And this prime divides the following number. I've got string of ones into some power of 10. Okay, and I've assumed that n is not 5. Okay, n is a prime number, that's not 5. So maybe I should also assume Okay. So actually for this, I should also assume it's not a prime number. It's not 2 also. Because I changed the problem, right? I only want ones in my decimal expansion. If I ask for that, then n equals 2 also is not going to work. Because any multiple of 2 is an even number. So it cannot have only ones in its decimal expansion. So let's change our problem a little bit. N is a prime number, but n is not 2, n is not 5. For those two, this is not going to work. But for all the other primes, this is going to work. Okay, why? Because I assumed n is not 5 or 2 and n is a prime number. Okay, so now can you complete the argument?
So n should divide the 1, 1, 1.
Correct. So observe that this 10 power I is nothing but 2 power I into 5 power I. So those are exactly the prime factor. If you write the prime factorization, it has 2 power I and 5 power I in it. N is a prime number and n is not 2 or 5. So those two possibilities are not there. N is not going to divide this portion of the number. So n only has to divide this portion. There is no other way. Okay, so we are just using this one. So n actually divides the j minus. And that's n. Okay, so this was just to demonstrate that the proof actually gave us a little bit more, which we didn't need initially, because we were only originally trying to show there exists some multiple. But if you have to sort of do a little more, be somewhat more detailed, get more detailed information, then in this case that was also available. Okay, now let's do the next principle, which is slight generalization. So this is called the generalized pigeonhole principle. Just a mild generalization of the previous idea. Again, the same, philosophically the same thing. So if you put, so okay, let me just do it by example. So if you put 43 objects into 8 boxes, okay, into 6 boxes. You put 43 objects into 6 boxes. Okay, so observe, this is not the usual pigeonhole principle in the sense there it was n boxes and n plus 1 objects. Here the number of objects is much more. Then what can you do? Any suggestions on? So I want to make a pigeonhole principle type of conclusion.
Delta X is placed one box
Yes.
which contains more than 7 objects.
Okay, excellent. Then there exists at least one box containing strictly more than 7 objects, meaning at least 8 objects. Okay, why is this? Because, well, let's prove it. Suppose not, let's do it by contradiction. Suppose when you distribute these 43 boxes into these 43 objects into these 6 boxes, suppose every box only gets fewer than 7 objects, then 6 boxes, everything having maximum 7 objects, that's only 42 objects, right? So that's, you're given that there are 43, so at least one of the boxes must have 8 objects. Okay, so the proof is just by contradiction. Just proceed by contradiction. And you're done. Okay. So this is sometimes called the generalized pigeonhole principle because it says, it also gives you some sort of a number, a lower bound on how many objects there are in the box. Okay, so let's see if we can use this in various ways. So here's problem 4. So among 100 people, if you take a group of 100 people, there exists at least 9 who are born in the same month. So how do we use generalized PHP to prove this? So number of months, possible different months, there are only 12 different months. Okay. Suppose this weren't true, if there were only 8 or fewer, if there were, so if the given conclusion is false, if there were less than or equal to 8 people born in every possible month among these 100 people, then how many people are there? Then the number of people in the group is, well, there are at most, so there are 12 months, and in each month you see how many people have a birthday in that month. At most 8 people are born that month. So this means that the number of people in the group can be at most 12 into 8. Okay, and that's only 96. Okay. But you're given that there are 100 people in the group, so this is a contradiction. Okay, so this is just an instance of the same thing. Okay? If there are more people, then there has to be more overlap. Okay, and one can sort of formulate this as a general thing. So in general, you will often see this sort of thing. I have n objects. So n objects distributed into k boxes. Okay, k is usually smaller than n. Then at least one box, then there exists a box containing at least how many objects. You divide n by k, and when you divide, you will get some. It's not always perfectly divisible. It can give you an integer, or it can give you an integer plus some additional fraction. So if it gives you some fraction, so you take what's called the ceiling function. So this is not the greatest integer function, but it's the number that's the integer that is the smallest integer that's greater than or equal to n by k. So this is sometimes called the ceiling function. And what's the ceiling? The ceiling is just so ceiling of x. X is any real number. Ceiling of x is the smallest integer that is greater than or equal to x. So in this example, I have 100 people and I have 12 boxes in 12 months. If I compute 100 divided by 12, well, that's 8 and 4 by 12, right? So that's 8 and 1 by 3. That's my number. So the ceiling function means I must take the next largest integer. If it's already an integer, then I take that integer itself. Otherwise, I take the next bigger one. In this case, it's just 1. Okay, that's exactly this. Okay, now any questions on this particular problem? Okay, now one can actually sort of rephrase this in a different manner, in which you don't.
So in this case, the capital N is bigger than small k.
Sorry, what?
The relation between small and k should be small k is smaller than, right?
Small k is small, yes. Otherwise, of course, I mean, this is still true. If you see what you will get in that case, n by k will be 1. Okay. See, if small k is bigger than capital N, then the ceiling function is 1. So it is saying there's at least one box which contains at least one item. Okay, which is sort of obvious, because there are totally there are totally n objects, so at least one box should contain one. Okay, so it's sort of trivially true also in that case. But in examples, typically k number of boxes will be fewer than the number of boxes. That's the usual situation for the Pigeonhole Principle. Okay, now so sometimes we can turn this around in the sense that we just like the previous problem, you have a group of people and you want to conclude something about how many of them are bunched together inside a single box. Right? So here's the here's a slight variant of this question. So let me write this out. So we want to organize a meeting. A meeting of n people. Okay, so I want to invite capital N people to a meeting. Now, what is the smallest value of n? What is the smallest n for which we are guaranteed that there will be two people among these n people. There will be at least two people born in the same month and whose names begin with the same alphabet. Okay, so is the question clear? I've sort of made this slightly more complicated than before. So I not only want them to have the same birthday month, I also want their names to begin with the same alphabet. Okay, and I want to know how big a group should I call. Any suggestions?
13 into 27.
Sorry, what?
13 into 27.
27. Okay, excellent suggestion. Let's just see how you got there. So suppose we only put the first condition. Okay, so suppose only require. Sorry, yes. Presentation visible? Can you see my presentation now? Okay. So suppose I only put the first condition, only require that I want to be guaranteed that there will be at least two people with the same birthday month. Okay, so if I only require the first condition, then how many people should I minimum invite?
13.
13. Okay, then the smallest n is 13. N equals 13 is the smallest. Suppose I only want the second condition to be true, that I want to be guaranteed that some two people will have the same initial first letter of their names will start at the same letter.
27.
So I should have at least 27. Okay, but now I'm saying something more. I want two people with the same birthday month and the same initial alphabet. Now I'm asking what is the minimum n for that? So how did we get this? This is 12 possible birthday months to which you added a 1, right? That's how we obtain this number. Now, why 26, 27? Because there are 26 different alphabets, and I should add one more so that I will ensure that there will be overlaps. Two fellows will have the same starting. Now, use the same reasoning. So it's not 13 into 27, but it's something very close. I mean, the idea is right. So if I need both conditions, then how should I argue?
$27.
Sorry, what? What is the answer? If I want both conditions to be true.
27.
Why only 27? 27 is only for the second condition.
12 into 26 plus 1.
Absolutely. It's 12 into 26 plus 1. Okay. Could you just explain your reasoning? How did you get this?
Birthday alphabets. So January.
Okay, very good. So look at all ordered pairs. So on the one, you write out the birthday and comma the starting letter of the alphabet. So January A, January B, and so on, like that. All the way till last will be December Z. Right? So these are all the possible configurations, all the different choices of ordered pairs, because I'm now keeping track of two pieces of information, their birthday as well as the starting letter of the alphabet. So I must write out how many total possibilities there are for that. So that is 12 into 26. 12 possibilities for the month, 26 for the starting letter. And then to that I should add 1 to ensure that there will be overlaps. Right? The generalized pigeonhole or pigeonhole principle, that some two fellows in this crowd will have the same pair of birthday and starting. Okay, so that's the answer. It's 12 into 26. Okay, great. Okay, so let's do some more. So this is a slightly complicated example, but again, it demonstrates the power of this pigeonhole principle in general. So here's the question. So let me write it out again. So let n be a natural
So
number.
the previous example,
Yes.
we have same month, right? Or in the question?
No. I have listed all of them. December A.
Yeah. That's okay. So what is our aim? So the conclusion says there is at least 2%.
Yes.
Have same, but okay. Well, just to go the previous slide.
Yes.
To say.
Same birthday month, who are born in the same month, and both conditions should be simultaneously satisfied.
Okay, so we say that there is a overlap, right? Suppose one is in the January column, suppose in another one is in the December column.
No January column, December column and all. So what I'm saying is, look at this set of, so for every person, so let's think of it like this. There are 12 into 26 boxes. Okay, those are my pigeonholes. I form 12 into 26 boxes. So first box will be fellows born in January whose names begin with A. Second box, fellows born in January whose names begin with B. Okay, so let me just do that all the way like this. So I list all these boxes, etc. Till the last box will be, I will put everybody who is born in December whose names begin with Z. Okay, this is all right. So I have 12 into 26 pigeonholes, 12 into 26 boxes. Now, I have a group of n people. So what am I going to do? If I have, for example, I choose n to be this number, 12 into 26 plus 1, then for each person, I will put that person in the appropriate box. So I'll take somebody, if they are born in, say, March, and their name starts with A, I will put them in that box. Okay, March with starting letter A. Right. Then next fellow comes, his birthday is some month, his name starts with some letter, I put him into that box, and so on. Okay. Like that I keep doing to all these many fellows, 12 into 26 plus 1 people. I will distribute them among these boxes, but there are only 12 into 26 boxes. Right. So what does that mean? When I distribute, some two fellows will have to go into the same box. Right?
Okay, got it.
Is that all right now? So that means those two fellows have the same birthday and the same starting letter. Yeah? Okay. So basically what you have to always do is first find how many different configurations there are and add 1 to it. That's the way you find the smallest possible number n, which will give you an overlapping configuration. Okay, so here's another example. It says let n be at least 1. And the statement is that prove the following, that prove every sequence of real numbers of n square plus 1. Every sequence containing n square plus 1 distinct real numbers. Contains a subsequence of length n plus 1 that is either strictly increasing or strictly decreasing. Okay, so let me explain this question a little bit by an example. So suppose I take n equals 2. What I'm saying is, I first look at a sequence of 2 square plus 1, which is 5 numbers. So n square plus 1 is 5 in this case. So what I have to do is to write down a sequence containing 5 real numbers. Okay, so I can take them to be integers, whatever it doesn't matter. So here is an example of a sequence. So I write 3, -1, 4, 2, 0. So I've written down 5 distinct real numbers. Now, what you're asked to do here is, it says you have to look at subsequences of the sequence. By subsequence, it means the obvious thing. You take only some of the terms, not all of them. You have it claims that you will be always able to find a subsequence whose length is n plus 1. So in this case, n plus 1 is 3. So claims I can find a subsequence of length 3, which is either strictly increasing or strictly decreasing. Okay. So let's do this. So let's take, here's a subsequence 3, 2, 0. If I just take these 3 terms, so subsequence doesn't mean it must be consecutive terms. I can take any 3 terms in that order. I can skip terms in the middle. So 3, 2, 0 is a subsequence which has 3 terms and it is strictly decreasing. Okay. And of course, there could be more than one such possibility. For example, can anyone see another one? So here's another one. 4, 2, 4, 2, and 0. Is my presentation visible? Slide?
Yes, sir.
Did it go and come in the middle?
No.
No.
It was always visible, is it?
Yes, sir.
Okay.
Yes.
Okay, good. So here is another subsequence 420, which is also subsequence of length 3. And these are strictly decreasing subsequences. In this case, you cannot find any strictly increasing subsequence. Yeah, because you see, what are the possibilities? If I start with -1, then if I'm 3 fellows, I can't. -1, 4, -1, 2, 0 is not increasing. -1, 0 is only length 2. So here I'm not able to find any strictly increasing subsequence. Okay, all I'm able to find are strictly decreasing subsequence, but there are 2 of them in this case. Okay, so let's do another one. Maybe n equals 2. Maybe somebody can just choose some 5 random numbers and so just tell me some numbers. Let me write them out. Let's check whether it works in that case.
E pi root 2.
Root 2.
1 by 2.
Huh?
1 by 2.
1 by 2 and
-8.
-8. Okay, wonderful. Thank you. So here are 5 numbers. So okay, let's just write their values because we need to compare. E is 2.71 dot dot, Y is 3.14 dot dot, 1.41 dot dot, 0.5. That's -8. Okay. So can we find a subsequent? So this is just a random sequence for now. Can we find a length 3 subsequence which is either increasing or decreasing?
You can take decreasing. E root 2 1 by 2.
Very good. Okay, those 3 will do. E root 2 1 by 2 or E root 2 minus 8. Increasing in this case is also not there. Yeah, there doesn't seem to be any increasing there, but at least one decreasing subsequence we found. Okay. Okay, wonderful. Thank you. So and so on. So the statement here is that this will always work. If you just write any random set of 5 distinct real numbers in sequence, out of them you'll be able to find a subsequence of 3 numbers such that they will be either in strictly increasing order or strictly decreasing order. Okay, again, somewhat slightly counterintuitive. I mean, it seems one should check many examples before one starts to believe that something like this could be true. Okay. But again, the proof itself is some miraculous application of the Pigeonhole Principle. So let's do this. It requires a little bit of setting up, little cleverness in trying to put it into the Pigeonhole formulation. So let's do this. So let me take the one I had initially, 3 minus 1, 4, 2, 0 as my example. So I have 5, here's a 5 term sequence, right? N square plus 1 terms. I have 5 terms. Now here's what I'll do. For each dot, I'll think of these as the 5 terms. So to each dot, I will associate a pair of numbers, just like we did that January, comma, A, B, like that. There are 2 parameters to keep track of. So let's define those 2 parameters. So for each point, I will define a number called I and a number called D. So what is I? I is the following. It is the length of the longest strictly increasing subsequence, which starts at that point. Okay, so let's suppose this number here is X. Okay, this is the second number subsequence starting at that point X. Okay, and D similarly is the length of the longest decreasing subsequence which I can find inside the sequence, again which starts at X. So it has to start at X and you look to the right. Okay, so I define a pair of such things. So let's see what are I and D in this example. So let's take this guy -1. Okay, what is I for it and what is D for it? What is I? The longest increasing subsequence which starts at this number. So let's see what will that. So -1 and then
either
4 or 2 or 0. I can take any of them, but that will only give me length 2. That's all. Right? I can never find 3. So here I is 2, and what is D?
0.
0. Well, we will call that term itself as one term. Okay, let's not call it 0. Let's call it 1. Right. So -1 is the first term of the sequence of the subsequence, but I cannot find any. There is no second term here because everything to the right of it is bigger than -1. So I cannot find a strictly decreasing subsequence of length more than 1. Okay. So here I is 2 and D is 1. So let's do it for each of them like that. So let's take the second fellow. For 4, what's the length of the longest increasing subsequence?
1.
1, because 4 is the only term, and then decreasing
3.
3, 4, 2, 0. For this guy
1.
1,
2.
0,
1, 1.
1, 1. This is left. For 3, what's the longest increasing subsequence? 3, 4.
3.
3 and 4 is an increasing subsequence. Right? So 3 and 4. So that means that's 2. I can't get anything bigger than that. So is that all right? 2, comma. What's the decreasing subsequence length?
320.
320. Okay, so is this all right? So what we have done, so and this is somehow the clever part of the proof, which is sort of non-obvious how to come up with something like this. But these are, so when you have a sequence, somehow you realize that there are these two pieces of information you have to keep track of. Starting with that point, what's the longest increasing subsequence I can get, and what's the longest decreasing subsequence I can get. Okay, now let's look at, so this is how you form these numbers I and D. Okay, so now let's just shift to the general case. So what's my general case? I have n square plus 1 numbers. So n square plus 1 dots, right? So I have so many numbers. And for each number, I have an I and a D. From this number, ID and so on for every number. Okay, now what is it that we have to prove? We must prove that there exists a, show that there is a subsequence of length n plus 1 that is either strictly increasing or strictly decreasing. Yeah, so let's proceed by contradiction. Suppose now, suppose the conclusion, the required conclusion is false. So this is the first thing. We're going to proceed by contradiction. If the conclusion is false, what does that mean? It means that there are no subsequences of length n plus 1 which are either strictly increasing or strictly decreasing. What does that tell me about I and D?
Greater than or equal to n plus.
Greater than or equal to?
We are assuming that. At least contains.
This is what you have to prove, but remember I have assumed the contradiction that this is not true. I cannot find the subsequence of length n plus 1.
That is less than n plus 1 or greater than n plus 1. Okay, if we greater than n plus 1, we can take n plus 1. Okay, it's less than n plus 1.
Yes, so it is strictly less than n plus 1. So it's at most n. So observe, if you make, this is under our assumption. So maybe I shouldn't write this here. So see, what is our, that is, there does not exist a subsequence of length n plus 1. See, if there is no subsequence of length n plus 1, there is also no subsequence of higher length. Okay, because this a smaller subsequence will be contained in the larger, right, which is increasing or decreasing. It's strictly increasing. Okay. What does that mean? It means that this, for every dot, the I and the D values that you are every dot in my subsequence, by which I mean for every one of these terms in my in my original sequence, for every point x of my original sequence, maybe I should try for every x of, for every term x of the given sequence. Maybe I should have labeled it as I of x and d of x and so on. But let's not make it too formal. So, so for every term, I assume under my assumption, I conclude that I and D can be at most n. What does that mean? What are the possible values of I and D? Therefore, possible values of the pair ID. What are the possible values? It's like our earlier January A kind of thing. It can, both can be 1, 1, 1, 1, 2, 1, 3 till 1 comma n, blah blah blah, all the way till n1 till nn. Right? So this is the full list of possible values of ID, and how many total possibilities are there? So number of possible values is
n square.
N square. There are exactly n square different possible values. But the sequence has n square plus 1 terms. Okay, that's where the pigeonhole principle comes in. But given sequence, the original sequence has n square plus 1 terms. What does that mean? By pigeonhole principle, this means that there exist two terms, at least two terms, call it x and y, of the original sequence such that what happens?
Same I and D.
Same I and D, absolutely. Such that I and D of x matches the pair I and D of y. So remember, this is exactly like our earlier problem with birthday and name. So they both have the same I and D. Okay. So what does that mean? So I have a sequence like this. X is somewhere. Let me assume that x is smaller than y in the sequence. Again, I can do that without loss of generality. Because if not, I will just rename them as y and x. So here's my sequence. I have 2 points. I'm claiming the point x. I am concluding that the point x and the point y both have the same I and D. I claim this can never happen. This I and D is actually a very beautiful sort of numbers. It can never happen that two elements of the sequence have the same I and D. It will always be different. Okay, so let's prove that. So claim this is impossible. What is impossible? That I and D of x and y are both the same. Okay, let's prove it. Proof. Okay, so what is the proof? So I've assumed, remember, that x is smaller than y in this sequence, right? So I've assumed that x is the smaller element. So let's look at the I of x. Okay, so what does the I for x mean? It means that starting at x, what is the longest subsequence? So same for y. So let's look at for y. Let's look at what is its. Sorry, what am I supposed to do? I'm supposed to take the. Okay, so let's look at the longest subsequence of longest increasing subsequence starting at y. Okay, so I start at y, and there is some increasing subsequence which starts there, right? So there is a bunch of terms like this. So let's say that this is the longest increasing subsequence starting at y. So longest. Okay, but I claim then that the value of I for x cannot equal that of y. Sorry. That's something I made a mistake there. See, x and y are some two terms. So I just said assume without loss of generality that x is smaller than y. So that's not quite right. See, x is x is to the left of y. I mean, I'm just calling the term which occurs to the left as x and the term to the right as y. But remember, my original sequence was a random sequence. I could have written numbers in any order, right? So there are two cases to consider actually. So case one, the number x that I have is smaller than the number y. Okay. So if this was a 3 and that was a 4, for example, then I claim that the I values of these two cannot be the same. Okay. Why? Because look at the longest increasing subsequence which starts at y. Okay, it is y, and then the next term is bigger than y. Let's call it y dash. Next term is even bigger. Next term is even bigger, and so on. Right? But since I know such a thing exists, what I can do is the following. I can attach one more term to this subsequence. Take that same subsequence and put one x in front of it. Okay? So consider, so if y dash, y double dash, etc. is the longest increasing subsequence starting at y, then consider the subsequence in which I just append an x to the left, x, y, y prime, y double prime, and so on. consider this sequence, this is also increasing. Why? Because I assumed in this case that x is smaller than y. So this is still an increasing sequence. So this is also an increasing sequence. But then what does it tell me about I of x? The I value for x, therefore, has to be at least the I value for y plus 1. Is this all right?
Yes.
Because what I'm saying is take the subsequence which gives you I of y. So this is the longest increasing subsequence starting at y. Means this subsequence, its length is exactly I of y. Right? That's by definition the longest increasing subsequence starting at y. And now to that I am able to attach one more term. So that means the longest increasing subsequence for x, its length is at least one more than this, because here is one candidate subsequence. Okay. And similarly, so this is a contradiction because we assume the I values are the same. Similarly, if case 2, if x is greater than y, okay, the number which is on the left is more than the number on the right, then we do the same thing for the decreasing subsequence. Then you can see by the same logic that if I take the longest decreasing subsequence of y, so I do the same thing. So I have x here, I have y, and I know x is bigger than y. And for y, I have a longest decreasing subsequence, that is some y dash, y double dash, y triple dash, like that. So that this is bigger, this is bigger, this is bigger. Now I take the subsequence which gives me, so take this is just the subsequence which is decreasing of length exactly d for y, the maximal length decreasing subsequence which starts at y. Take that and you attach an x to the left of it. Now what you get is it's a longer decreasing subsequence starting at x. Okay, and therefore d of x, which is supposed to be the length of the longest decreasing subsequence starting at x, this is at least the length of this one candidate that I have produced. This is at least dy plus 1. Okay, it's again a contradiction because I assume to start with that both I and d are the same. Okay, so again a very sort of tricky in some sense application of the Pigeonhole Principle, but always, I mean, you can see that you can prove some very somewhat counterintuitive results just by realizing that there are always more objects than that there are boxes. So overlaps have to occur, and then after once you conclude that overlaps have occurred, then you sometimes have to do a little bit more. For example, here we realize that I and D being equal can never actually happen for sequences. And so here's sort of a sort of follow-up question: what if the sequence only had n square numbers? What if the original sequence did not have n square plus 1, but only n square numbers? Then is the same conclusion true? Then is it true that you can actually find a subsequence which has exactly, whose length is n plus 1, which is increasing or okay. So the Pigeonhole Principle requires n square plus 1 terms, but what is the situation for n square? Can you produce a counter example, for example? Okay. So please do think about this for the tutorial tomorrow. Try to see if you can produce counter examples for this particular problem where you assume you only have n square terms. Okay, so I guess that's time. So maybe I'll stop and we will sort of do maybe more problems of this kind in the tutorial. I'll just send out the extract from the book which deals with this particular section, so that there are many more problems which you can look at. Maybe come with questions and doubts for tutorial. Yeah. Okay. This one.
Hello, sir.
Yeah. Yeah. So it's fine, right? I'll stop. It's almost 7.
Okay, sir.
Yeah. Okay. Thank you.
Okay, sir. Thank you, sir. Thank you.
Thank you, sir. Thank you.
Thank you. Yeah.
Thank you, sir.